Okay, here we are in note set 3 in our unit 4 on reverb. Remember, that's what the RVB stands for. And this is our second note set dedicated to implementing convolution reverb. But remember, the first one was just a preliminary result. It wasn't successful in establishing a way to do convolution reverb in a real-time, computationally efficient way. So it got the efficiency part, but it did not handle the zero latency part. In fact, it made the latency worse. So now we are ready, though, to extend the overlap save method that we saw in the previous note set that reduced the computations but worsened the latency. We're now ready to put that together with some other ideas to finally come up with an efficient zero latency method to do convolution reverb. And I am basing this on a paper by William Gardner. Came out in the Journal of Audio of Engineering Society in 1995. Around that same time, as I mentioned in an earlier note set, there was another paper that I think was independently developed by two other people. I've not read that paper, but I took a quick look at it, and I think it's pretty much the same as what Gardner came up with. Maybe there are some slight differences, but that's pretty much it. But Gardner's paper is really the standard by which I think most people in the audio world go by for convolution reverb. So not only did he publish this paper, but he also worked in the field and is quite a big name in the reverb world. In fact, this whole unit on reverb is largely based upon, aside from this particular note set and the details for convolution reverb, the overall view I based largely on a chapter that William Gardner wrote in an edited book on audio signal processing. So, big name. So let's look at what we're talking about here. So far, we've looked at two methods for doing convolution reverb, neither of which actually worked. Just because they're methods doesn't mean that they're actually viable. It's just a way of computing it, whether it meets your needs or not. So let's let n sub h be our filter length. And so the first way we said was, hey, let's just do it by direct FIR computation. So every output sample is NH filter coefficients times NH input samples. So the number of multiplies per output is NH. Then you add up all those products and put it out. And if you can do that computation within the time between one sample, then you have zero latency. But really, there's nothing algorithmically that makes you have to wait. It's just a computational processing power issue, whether you can meet that latency or not. Then we looked at the overlap add and overlap save, and in particular, we're going to be focusing on overlap save here. And that was applied to the whole impulse response, so length NH. And what we saw was that it significantly reduced the number of computations. So that's good. But we also saw that it led to a very large latency. I put that in capital, bold, underlined word there, large. So that is not really suitable. But what we'll see is that we can take overlap save and extend it and come up with a way that we can handle both of these issues. So here's a plot that we looked at before, and this is from Gardner's paper. What he's referring to here as large block is this overlap save applied directly to the whole impulse response. And he's only showing out to filter sizes of 1024. If you think about a sampling rate of 44,100 samples per second, usual reverb lengths are 100 times that. So 100,000 samples, something like that. That would be a roughly 2-second long impulse response. And that's not unusual for some rooms that we're interested in. But you can see that the latency is proportional to the filter length. So if we go out 100 times that, it's going to be 100 times that. So we're into the seconds, not milliseconds at that point. So completely infeasible. And this, we see this just keeps growing. And remember, we have to go all the way out here. That becomes huge. So this is infeasible unless you have a super fast processor. And remember, reverb's not the only thing you're going to do, and you don't want these units to be unaffordable. So that's not really feasible. So we need a better way to do this. And so fortunately, Gardner's paper back in 1995 laid out the ideas for doing that. And here's the key idea. This is the big recognition that led to this idea. The reason that the overlap save or even overlap add did not work is because the filter is very long. So remember we said, the direct DFT-based method, the simple DFT-based method didn't work because the signal was too long. So then we chopped up the signal. Now we're saying the filter is too long for this type of application. For other applications, maybe not, but for reverb, the filter length is long. And so the key idea is, well, if it was good to break up the signal into blocks, it's going to be good to break up the filter into blocks. So let's put aside for the moment any thought of overlap add and overlap save. Let's just think about we need to convolve a signal with this input or with this impulse response. And we break it down into a sum of non-overlapping blocks. We looked at the mathematics of that, how to write that out mathematically for the overlap add case. So I didn't go into the details, but each one of these is just something that is non-zero where the other blocks are zero. So that means if we convolve X with H, and again, this is just Peratt's notation for convolving something. That means that since convolution is linear, we can pass the convolution through the sum. So we would convolve X with each individual block and get a Y sub K from each of those, and then just add up those individual outputs. So a bunch of output components that would add together to give the complete output. So that's the first idea, and that's the biggest one. The rest is just trying to figure out how to mechanize that and make it feasible and workable. So the second idea is that even though we said these are non-overlapping blocks, we didn't say anything about their sizes. So the idea here is to pick the blocks so that they grow larger later on in the impulse response. So one choice, and we'll see that this is not necessarily the best choice, but it works, is you can see how it escalates. Our first block is n, then we have n, then 2n, 4n, 8n, 16n, and so on and so on. And Gardner says, a typical n value for typical DSP chips at that time was 32 or 64. So with today's processors, the choice of that value for n might be different. But once you learn how to do this and you understand how it gets put onto a chip, you can determine what might be the best choice of n for your particular application. And so here we show that partition. So here's the X, that's our signal. That just keeps on streaming. And here we're showing a fairly short impulse response, just so that we can more easily see it. And we've broken it into 3 blocks. following this structure. So we've got n samples, 2n samples, and 4n samples. And down below, I'm showing what happens when we do each of these individual convolutions. So remember, this H1 has, we imagine it has some zeros out in front. So when we start convolving that with the x, just think about flipping x and sliding it. We have to slide it n samples before it even starts interacting with that. So this first y1 isn't going to start until n. And the y2 won't start until 2n, the place where h2 starts. And so on and so on and so on. So that's a good view to keep in your mind. Now, we start to see that, oh, we're kind of shoving some computations that we have to worry about further down the line. So when we're worrying about computing outputs in this time range, even though we might have many of these things, initially we only have to worry about those. And so that's kind of one of the things that we'll have to keep an eye on here, is how to mechanize all this. So again, I'm pointing out a key thing to keep in mind, that y sub k starts at the time point where the corresponding impulse block started. So keep that in mind as we go through here. So the third key idea is that we're going to look at all these different blocks, but the first one, H0, will be done in direct form. That way we'll ensure that we beat the latency issue. That one we'll see has to be done every sample so that it's available and coming out. That will leave us time to work on all the other ones in a more quote unquote relaxed way. And so this is important because the very first output sample comes from that one. We don't have time to collect some samples and do any overlap save processing because we need that first output sample right away. So we'll do that in direct form. But hey, that first one is just n, right? 32, 64. So that means we're only going to need about 32 or 64 multiplies per output sample. So that's in between every incoming input sample. So that would be doable. Fourth key idea. So we do H0 with the direct form, but all the other output streams, so Y1, Y2, and so on, are all going to be computed using overlap save. And I'm showing a picture right out of Gardner's paper. And I'm showing it mostly because you can do overlap save exactly the way that we talked about before in the previous note set. But Gardner has a slight twist on it. It makes no difference in computational complexity, and it makes no difference in the results. It's just he puts things in different places and takes results from different places, but everything works exactly the same. So here's the idea. So let's let the kth filter, so h sub k, whatever it is, be size m. So m is now meaning either n or 2n or 4n or 8n, whatever. So let it be m, and we'll just write everything in terms of m. So whatever m happens to be in terms of n. We're going to take that filter that is size m and zero pad it out to 2m. So remember, in overlap save, we zero pad the filter, but we do not zero pad the signal. Then we're going to use a 2m point FFT on the zero padded filter. Then what comes into it for the signals? We have a new signal block that's going to be size m. So we put that here. And then we have the previous, I guess I don't show that here. Yeah, I didn't show that. So that's the new signal block goes here. And we have, remember, overlap save uses some previous samples because the input blocks are overlapped. And so that would be the previous samples. And so for the very first time doing this, remember we fill this with zeros. So there would be some zeros out here, and how many zeros we put there would depend on which H we're actually working on. So our total signal size will be 2M, and we would compute a DFT of that. So here's the idea. Here's showing the pre-computed filter with the zeros padded at the front. That's backwards from what we did in the last set of notes and what most people do for overlap save. You put the zeros at the end, compute the DFT, but Gardner puts the zeros at the beginning. Then we take all of our signal samples, the new ones and the previous ones. We do a 2M point DFT. We form the product. We do the inverse DFT. And then Gardner discards the second half and keeps the first half. Again, that's backwards compared to what we did in the previous note set. In the previous note set, we did what most people do for overlap save. They discard the first part and keep the last part. But here we need to keep the first part because we put the zeros in front. It just works out that way. So just keep that in mind. But you could do it exactly the way that we did it. It's not going to make any difference. You just need to know when you put zeros in front, you keep in front. When you put zeros in back, you keep in back. That's all you have to remember. Okay. So what is this breakdown that we just looked at that I said it is valid, it's viable, but it will not actually work? And we'll see why it won't work. But it's called the minimum cost zero latency algorithm. And again, I'm just pointing out that back in 1995, Gardner said, you know, for today's DSPs, 32 or 64 for N was a good choice. Again, that your mileage may differ. So let's look at this decomposition. And this is what Gardner called the minimum cost zero latency algorithm. So what he argued was that with this decomposition, you can still get zero latency, and it is the one decomposition that will give you the smallest cost, the smallest number of multiplies and computational complexity. But so the idea is this grows very fast. And we'd like to have it grow even faster than that because it will reduce the amount of complexity that we need. But we can't go any faster than this, as we'll see. So here's the idea. Remember, this first stream is being done with direct form. So every input sample that comes in, we just compute a new output sample in this using just regular direct form implementation. Now let's look at the first chunk of the first stream, not Y0, but Y1 is what I mean by the first stream, the first non-direct stream. That's going to be computed versus overlap save. And what do I need to do? Well, I need to collect the first N input samples and tack some zeros on. So I'm collecting up to this point. But now notice that the outputs have to be available here. So the output has to be instantly available. So that means I collect up to this point, and as soon as I finish collecting that point, I have one sample time to compute the DFT, do the multiplication of that DFT with the impulse response DFT, do the inverse DFT, grab my desired chunk, and put it out to the output so that that is available right there. That's a lot to do in one sample time. And that happens every time at one of these boundaries. So this one here, to compute this block, I have to collect up to here. So I would collect the first 2N input samples. And in this case, I'd have a bunch of zeros as well. Now I need to compute the DFT, do the product, do the inverse DFT, all in time. I've collected up to here. I've collected up to here. And this needs to be available right there. So I have one sample interval to do all that processing, and so on and so on. And I'm not even talking about what's going on further down the line, but it's just a repeat of that kind of idea. We collect up to a certain time, we get all of our input samples, and we've got one sample time to compute and spew out, and that's a lot of computation to do, much more than we might have to do in the direct form. So yes, we can meet the zero latency, but it's at a cost. And we'll look at this in a little bit more detail on the next slide. So in each one of these cases, we have just one sample time to do all this overlap save processing. And so it does meet the zero latency requirement, but we're going to need a pretty hefty processor to do it, as we'll see. So yes, this minimizes the number of flops, floating point operations per second, and gives us zero latency. But remember, what good is having the minimum number of, well, I shouldn't actually say floating point operations per second. It minimizes the number of operations per block, but it's going to require more processing power because that processing power is needed non-uniformly. So here's what I mean. I've just kind of guessed at what these things would be like, and I haven't really accounted for everything, but you'll get the idea here. So what's happening? So remember, this is just doing the direct. So when we first start off, we're just processing these things. And so here is the processing load. That's how many operations we have to do per second in our processor. And so that's the load level for the direct for doing Y0. But then while we're doing that, we're just collecting these things to do our first output block of Y1. And so once we finish that, we've got one sample interval to do all the computation. So there is a width of one sample interval, and I had to work super hard to do that. And then I'm going to do another one. And then now out here, I've got multiple things and my blocks are bigger. So I'm showing the spike gets even bigger. But the important thing is it's a spike. So that's the problem. It's impractical. Yes, you could do it, but it's going to require you to get a processor that can do all this processing in a short amount of time. So the processor spends most of its time just waiting to work hard. I always joke that this is how students do homework, right? The homework gets assigned and you just sit there, don't do anything. And then the night before, or even the day of, or even the night of the due date, you then work super hard to do that. Wouldn't it be better to spread that out? As soon as the homework is assigned, you start working on the parts that you can do, and you'll have a much more uniformly spread out effort. I don't think students think like that. But in this processing world, it's better to uniformly distribute the processing load. That means you can use a lower speed processor. A processor with a lot less computational power would be required. Or alternatively, all that other processing can be done for can be used for other things. And so this is not a good way to do that. So let's look at this uniform demand requirement while simultaneously getting zero latency. So what we're going to do is just look at the first two blocks. Let's say that we let H0 be L samples, and let's let H1 be M samples. And we want to look at what happens with as we change the relationship between L and M. So let's look at this case. So an M point H1 block that starts L points into the filter response because H0 is L points. So using the ideas that we just talked about, that we know that we're going to have to collect samples up to time m, because we're going to need m samples, m new samples for that. So we wait and collect our m new samples. And we know that since this thing happens here, starts here, we know that the output from this block has to be available by time L. Okay, that's so that we can provide our output samples. We just saw that on the previous slide. So that's what I'm showing here. Here's time, and we collect up to time M. So we've got our M samples that we've collected. It's M samples because the filter block that we're talking about has M samples in it. And then it needs to be available by time L. So this is the processing window that we have. And the wider that we make that, the lower this level can be, right? We can spread that processing out over time. Now, what ends up happening? So suppose we've made those outputs available at time L. Now from M plus 1 to 2M. So from here to here, we need to collect the next M samples. So while we're processing these, we are still collecting. That's perfectly fine. Those are two separate things. So we collect out to 2M, but now that has to be ready to be available at M plus L. So that's shown here. So again, there's the time that we have available to do that. And etc. So now I'm just showing the next one. We start collecting here. And we need to be done by here, and we stop collecting here, we need to be done by here. And this would continue on. So notice that with the way I've set this up, I haven't said what L and M are, but I'm showing a gap between L and 2M. Well, if we look at this, what we want is uniform. We don't want any spaces where I'm not doing anything, and then other spaces where I am doing things. So what we would really like to do is spread this out. Now this M is fixed here, so we need to look at what L needs to be. To spread this out, we need to move L this way. So that means L should be equal to 2M. So for a uniform load, we've just argued that each filter block size M should start at least 2M samples into the filter response. Now, we really only argued this for the first one, but a similar argument could be made for all of the other ones. So that means for this example, L must be at least 2M. Could be longer, but at least 2M. So that would mean L would be coincident with that. That would be the ideal case. So this is the minimum cost that we talked about, and we saw that that's not good because it leads to these short periods of excessive computation. And this rule leads to something that looks like this. Now, there are a few cases where we do take that at least into account. So you can check that. So here's one of length n, it's at least 2n in. Here's one that's at length n, but it's 3n in. So that still satisfies that. And we'll talk more about that. You can see that every even indexed one is more than the minimum that we require. And the reason that that's done is mostly to just make this easier to mechanize and keep all the blocks nice powers of 2 and things like that. So that's the uniform demand decomposition. And that's the one that we're going to focus on. The minimum cost, out of favor now. We would never really consider doing that. So let's just take a look at our uniform demand. So we start with 2n, and then we've got nn, 2n, 2n, 4n, 4n. I think you can guess what comes next. 8n, 8n, 16n, 16n, and so on and so on. So I'm just showing this here and providing this as a way to keep track of where do the output streams start, because we'll need to keep track of that and understand that when we get to figuring out how to do this with the overlap save. So remember, this is done directly, and it starts right away. So the output starts right there because H0 starts right away. But Y1 starts where H1 starts, and Y2 starts where H2 starts, and so on and so on. So I just put this in there so you can always come back and look at this and say, okay, I know where these streams are starting. Okay, now an important part of this is the scheduling, because we're now going to have to do this with overlap save, and we're going to have to focus on when we do things. So here is the uniform demand decomposition of the impulse response, and I'm just pointing out that that is practical. And up here I'm saying we're focusing on the scheduling. When do we do various computations? So this is very complicated from a programming point of view. So it's no trivial matter to put this onto a DSP processor. So if you're thinking, I've never programmed a DSP processor, but I'm going to do this the first time, probably not a good idea, because this is going to be multi-threaded and all sorts of difficult things. So probably not the best thing to try right off the bat. But let's look at this scheduling. So this diagram is our guide to when we collect and when we compute, and then from it we can also deduce where the output gets put. So all of that is embedded with these little codes. And so those codes are interpreted this way. The first number is the new data starts here. So you can see it's like 0. All these first blocks are 0. That's where the new data starts for those streams. And then you can see subsequent blocks keep going up. So you can work that out and think about how to break down from an overlap save point of view for a filter of this length. Okay. That's the first number. The second number tells us the filter block size. So you can see H1 has length n. So all of these have a second number of n. And H2 also has n. So all of these have a second number of n. H3 has 2n. So all of those have a second number of 2n, and so on and so on. That also tells us our DFT size, 2m. Now, remember, half of that data will come from new data, and we know where that new data starts, and half of it will come from earlier data. So we'll know where that goes back to just from this information. And then we know that if we do a 2m size DFT for an m size filter block, we know that we throw half of that away. So the output block size will be m. And so the only thing left is to figure out where to put that output block size. So we'll take a look at that. But we can deduce that from the structure and knowledge of where these things are and where those streams start. So let's look at this. We can now deduce from here. I'm going to look at this box right here. What is it telling me? It says new data starts at 0. So I'm going to collect from 0 to n minus 1. So remember, the number here is going to tell me how much new data I need. I need as much as the filter size. So I know that I'm going to collect from 0 to n minus 1, and I know that I need to have n previous samples, but since this is at the beginning, the previous samples in x will be zeros. So I need n zeros, and then compute. Where? When am I doing the computation? So remember, this time here for this diagram is about when things are computed. So it's the box lies between n and 2n. So that really means n to 2n minus 1. So the boundaries on the right side are always one less than the indication of where that boundary is. And then where does the output block go, right? The output block goes from 2n to 3n minus 1 because H1 starts 2n in, right? So that's where that thing would start. And the output size would be whatever is there. So it's n samples starting at 2n. So that's how we figure this out. Let's do another one. Notice that I'm doing the odd indexed blocks in these first two examples. So N0 is 4n. It tells me that's where the new data starts. M is 2n, so it tells me I need 2n samples of new. I also need 2n old samples, so they are the previous 2n samples. When do I compute? Well, this block is right here, 6n to just shy of 8n. And then where does the output go? Well, this is H3, and it's 3 blocks in, so I can figure out that that's going to have to go at 8n. But here's the easy trick. For the odd indexed H's, the output goes immediately after the computation is completed. You can check that that is valid and that's true. So you can see that here also. I finish computing just before 2n, and that's where my output block goes. I finished just in time. But remember, I had quite a bit of time. I had this whole block to work on it, not just one sample. Okay, let's look at an even indexed one. So H4, let's look at this block here. So 4n tells me where my new data starts. 2n tells me how much new data I need. So I go 4n to 6n. Notice that that's the same as the block right below it. Okay, 4n, 2n. Notice also that then the old data that I include is exactly the same. And I compute in exactly the same location, 6n to 8n minus 1. Same thing, because that block lies here between 6n and 8n. But then here's the trick. Because H4 is out here, it doesn't follow the rule that it's just one after there. It follows the rule that it's 2 after there. Or not one sample, but 2 blocks ahead. So we can figure that out based upon where this thing is located and where we are in the stream. But once you see how to do that, you'll figure it out. It's always these even indexed blocks are given an artificially early deadline. And the only reason is to just make it easier to lay this out in powers of 2 and to just make the scheduling structure simpler. There's no real fundamental purpose for putting that there, but it's convenient. So let's talk about the priority of our tasks. You'll notice that as we move further into the algorithm, we've got more and more things that have to be going on kind of at the same time. So, looking here during 4n to 5n, we need to be doing this one and parts of those two and parts of those two. So we've got 6 different tasks plus 7, because there's an H0 that I'm not really showing here. So, for this simple case where I only have out to H6, this is, kind of artificially small case just for illustration. But I'm already having to run 7 tasks at the same time. And they need to be prioritized because task H0, every time I get a new sample, I have to make sure that I process that together with all the appropriate past samples to compute the new output sample. And I've got 1 sample interval to do that. So these DSP chips, these processors, are interrupt driven. So we get a new sample and the DSP processor chip is told, got a new sample. And our algorithm has to say, when they get that, it has to go off and say, do H0, compute that new direct term output for H0. Then once that's done, so we need to have enough processing power to finish that quickly. and be able to come back and start doing the rest of the things that I need to do. So then I can start working on one of the block computations, and I should start doing whichever one is the most important, whichever one needs to be done soonest that isn't already done. So at every sample, or every boundary here, n, 4n, 5n, 6n, I get new boxes that come into play. So I need to be finished with, so by 5n, I need to be finished with both of those. I hopefully have made progress on those because I got two new ones that come into view now that I have to start working on. So this is a multi-threaded processing environment. So I have to be working on, I finish those two, I go up, I start working on these, and then suddenly I have to come back down and work on these. Then I finish those, I go back, I better start working on these to get those done by 6n, and so on, and so on, and so on. So, so I have to give the highest priority to the box with the closest deadline. Remember, though, that this box and this box don't have the same, really don't have the same deadline, okay? But we're asking it to have that just to make things a little bit easier. So you could actually relax a little bit, but it makes the programming a little more challenging. So the endpoint boxes have the closest deadline, they have the highest priority. So that's all these down here. Then these would have the next priority, and those would have, and so on. I'm only showing 6 of these, but this would just keep going up. So let's just look at an example here. Suppose we're at time 4n, we've done all of our collections. Our highest priority, and I'm not showing the H0. Remember, that is our highest priority. That every time I get a new sample in, I got to go off and do that. Then I come back and go, okay, I need to be working on these 2 boxes. Those are my highest priority. And then my next highest priority or medium priority would be the 3 and the 4 box. And then my lowest priority are the 5 and 6 box for this case. And so now at 5n, I have to have finished those. So those are gone. And so now these remain, maybe I finished those too, in which case I have a very fast processor. But maybe I'm not done with those, but these now become the high priority ones. And so even if I'm not finished with these, I have to switch to doing these. But you have to keep in mind when you switch, these and these now have the same deadline. So, so I better start working on those. So this becomes a very complicated thing, and I've just shown you what color-coded things I have to work on. And so at that point, by the time I get to 7, this should be done, this should be done, this should be done, all of these should be done, these should be done, and I'm left with those. Well, actually, at that point, I have to finish those, I have to finish those, and I have to finish those, all by the end of 8n. So a lot of details and difficulty in programming this. Interrupt-driven, multi-threaded, all sorts of stuff. I'm not a programmer. I would never be able to do that. Now, there are some details in the paper on when you get an interrupt to tell you to go down to a lower priority thing that is coming into view. You have to save your results for whatever you were working on. So there are some details on how to do that. And that's kind of crucial to this multi-threaded thing. That's all I'm going to say about the programming. I'm not a programmer, so not sure how how I would do that other than finding a good programmer who knows how to do this and telling them, I've got the algorithm for you, and now you need to program it for me. Okay, so we've talked about the uniform demand decomposition. We've talked about the scheduling. And we've seen that it's important that we be able to finish these tasks as quickly as possible. So that means we would love to find ways to minimize or reduce the number of computations required to complete those tasks. So here are all the tricks that Gardner put forth in his paper. So the first is obvious. We talked about this before. All the filter blocks can have their FFTs pre-calculated and stored. So none of those FFTs need to be computed. Now the rest are tricky and clever. So the second one is to reuse any signal blocks FFT that we've already computed that we now need for some other task. And I'll show you what that is. So here is the C below right here. So for example, let's start off at the beginning. We've got H1 here and H2. Notice they have the same notation, 0n. So if we go back and we look, they need exactly the same signal data, right? New data starts at 0, length of n. Old data in this case would be n zeros. So the FFT needed here and the FFT, or the signal FFT needed here and the signal FFT needed there are exactly the same. So don't recompute, right? You do it for this one, which is the most crucial. And then remember, this has an early deadline, artificially early deadline, but that's okay. I don't have to recompute the FFT. And that's probably one of the largest contributions to the what we need to do in any given task. So that's nice. And that works all over the place, right? H4 is going to have the same signal DFT that H3 is going to have everywhere along the way. So there and here and here and here. So we can share computations between them. And same thing between 5 and 6 here. Those two will have the same signal FFT, same signal FFT, same signal FFT. So that's really, really helpful. The third thing is all of our signal data is real valued, and FFTs are designed generically or generally to handle complex data. And there are applications where that's needed. But for audio, all of our data is real valued, and there are some tricks. I alluded to that in the previous note set, but here we're going to look at it in detail. There are some tricks that we can do to make things faster when we know that all of our data is going to be real valued. And then there's another little trick that says there are places where I will need a 2M point FFT that really comes from the same data that these two that are spread across two smaller FFTs. And so you might think, hey, if I took a block and I took another block and I did the FFTs of each of them, is there any way to take those two FFTs and just directly convert them into this longer FFT? That kind of makes sense that there should be a way to do that. And in fact, there is, and we'll take a look at that. So let's look at number 3 first. This is the savings because we have real valued signals. So let's take a look at how we can do this. And this is the most basic operation that we need to do. So if we can make it more efficient, we're going to be saving a lot of computational complexity. So here's the first thing that we can recognize is that one endpoint DFT can be broken into two n over 2 point DFTs. So the way we're going to do that is we're going to take the even indexed samples of the block that would go into this endpoint DFT, and we're going to take the odd index samples. We're going to compute a DFT of the even ones and a DFT of the odd ones, and then fuse those together into the one endpoint DFT. Now, that by itself is not terribly exciting. The second thing that we can do is these two n over 2 point DFTs can be computed at the same time with one single complex valued n over 2 point DFT. And so that saves some computation. So this first part I just call classic result number 1, and that's break one n point DFT into two n over 2 point DFTs. That might sound familiar. In fact, that is exactly what we did in the first step of the decimate in time FFT algorithm way back in Unit 1. So here's the idea. I'm given a block with n samples in it, and that would be its DFT, okay? I don't want to compute that directly, so here's what I'm going to do. I'm going to say, let's take XE and have it be the even samples of this block, and XO will be the odd samples of my whole block. Okay, so now I have an n over 2 point signal and an n over 2 point signal. Suppose we compute the DFT of each of those. So it would be n over 2 point DFT of that and n over 2 point DFT of that. So I'm going to denote those as this. Those are n over 2 point DFTs. And now here's the culmination of the trick. I can get the first half of my n point DFT by taking these two things and fusing them together using that formula. And I can get the second half of my full n point DFT by taking these two things and fusing them together this way. And this W sub n is that. So we've seen this. That is nothing more than the first stage of the decimate in time FFT. So I don't have to prove that to you. We've already proved that back in Unit 1. So let's visualize this. So here's the formula that we just stated, and it will end up looking like this. Here is the even indexed samples going into an n over 2 point DFT. Here are the odd ones. I only show the first two, the rest are obscured. And I do an n over 2 point DFT to get those things, and then they get fused together doing a 2 point butterfly. And that 2 point butterfly is going to end up looking like this. So notice the plus and minus here, that's there. And the WNK gets pulled out in front. That's just classic first stage of a decimate in time FFT algorithm. So we know that we can do that. And so this result by itself doesn't really do anything for us, because if we just did the full FFT, it's going to be in there. But by doing it explicitly, we're going to be able to do the second part of this trick. And that's this. So each of these n over 2 point DFTs, we can compute them at the same time with one complex n over 2 point FFT. And that's because all of our data is real. So let's just say, for convenience, we're talking about n over 2 point DFTs. Let's just call that size m. But remember, we're really going to be doing FFTs of size n and 2n and 4n. So if we were doing 2n, then m would be equal to n and so forth. But if we can do it for this case, we can do it for the other cases as well. All right, so here's our classic result. Do two m point real signal FFTs with just one m point complex signal FFT. This is what FFTs were designed to do. So if we can do the two things that we want in just one of these standard things, it'll be faster than putting each of these things into its own FFT. So let's just call these things XE and XO, because that's what we called them up above. And so here's what we're going to do. We're going to form a new temporary signal, call it G of n. And that G of n will have the even part as its real part and the odd part as its imaginary part. So now I have a complex signal where these two signals are still able to be separated, right? Oh, there's the real part. That's the even. Oh, there's the imaginary parts. Those are the odd index samples. So now suppose I put that into one M-point complex signal FFT, and let's call the result of that G of K. The question now is, now that I've computed that, can I get back the DFT of each of the two individual signals that I'm talking about? So somehow I want to take this and, without computing any more DFTs, generate the two individual DFTs I want. Now, here, these things are obviously sitting out in the open, real part and imaginary. But here they're kind of embedded in there, but still separable. That's the clever thing. Let's see how we can separate them. This is the claim. We take this thing, we take it, and we add to it its conjugate, but indexed backwards. So here, as we're going through our K values, we're going to go forward through this one and backwards through the conjugated one. And the same thing down here, the only difference is I'm going to subtract, and then they both have a half, and this one ends up with a J out in front. So let's see where that comes from. And I should point out, when we put in K equal to 0 here, right, we're going to have 0, we're going to have 0. So now we're going to have G star of M. Where do I get that from? Remember, DFTs are periodic, so GM is the same as G0. So you just have to keep that in mind when you're indexing through. So if we do this, we compute G of K and we use it to form this, my claim is that saves computation. I'm not going to go into how much computation it saves, but I think it's pretty clear. It's about 50%-ish. So I'm going to do a proof of this that's a little different than the proof that Gardner gave in his paper. The one I give is more classic from standard DSP books. Gardner's is, in my opinion, a little harder to follow. So let's take a look. Here's the trick. Remember, we put in the even part as the real part and the odd part as the imaginary part. So now look what happens. I can get back in the time domain my even by just taking that and adding its conjugate to it. What does that do? The conjugate makes this minus. So when you add them together, you get a plus J and a minus J. So they cancel, but I get two of those, and that's why I need a 1/2 out in front. And then same kind of thing here. Now I'm going to conjugate, but I'm going to subtract. So remember, when I conjugate, the real part will be the same here and here. So when I subtract, the real part goes away, and then I'll get double the imaginary part, and I need to multiply by a J to get rid of the J out in front and convert it into something actually real. So this is just pure algebraic trick. But that's the key to seeing how we do this. So now let's just say, well, here's the things that I want. So let's look at what they are in terms of these representations. So I never really do this. I just do this, but this is going to be our step to understanding how to break the DFTs back apart. So the DFT of G of N and the DFT of G star of N. And then I've got the J 1/2 out in front, DFT of G star, DFT of G of N. Okay, so, well, I know what these are. Those are the things that I'm going to say I compute, right? The whole point is take form G of N, compute big G of K. I've got that. So I've got that and I've got that. Do I have these? Well, there is a result. This is a classic DFT property. Just look in any classic DSP book, you'll find it. There will be a chapter in there that'll be like DFTs, and there will be something about DFT properties, and this is one of the things that will be in there. So if G of K is the DFT of G of N, what is the DFT of G star of n? That's going to be what this thing is. Well, it turns out it's just the conjugate of the DFT indexed backwards. Again, remembering that G of M, so when I plug in k equal to 0, that's really just G of 0 as well. Okay, so with that result, we end up getting what I claimed. So there we have it. So let's put it all together. Here's our trick number 3. We're going to do an FFT of an endpoint real signal using one endpoint complex FFT. Saves about half the computations, roughly-ish. So we start off with the samples in our block. It's an endpoint block, whatever that is, but it could be 2n or 4n, but we're focusing on the endpoint block, endpoint real signal block. We split it into its even and odd parts, so we would do that. These are the things that we're going to do. Previous few slides have been proving. Now we know the steps. Split it into the two parts. Form the G of n. This goes into the real part. This goes into the imaginary part. Now I've got a signal. So that didn't take too much computation. That's really just indexing and some, not even really adds, because you don't really add real and imaginary parts inside a computer. You just say, my G of 0 has this value stored in one memory location and this value stored in the subsequent memory location. That's how you do it. So we have that. Now I'm going to take that complex data and compute an n over 2 point DFT, right? I went from n points down to 2 n over 2 point things, down to 1 n over 2 point things. Take its n over 2 point DFT. I now have that. And now I need to extract the DFTs that I want. And so here's our two little clever equations that we came up with. And so I've got an n over 2 point and an n over 2 point. Those are the two things that I want, but that's just the first part of it. Now we have to use the first stage of a decimate in time FFT algorithm to fuse those back into the full endpoint DFT. So there's our little butterfly structure. So believe it or not, this saves computation. I know it always seems weird when you do these mathematically complicated things, but then they end up saving numbers of computations. It's really quite remarkable. Okay, so that's trick number 3. Trick number 4, quite a bit more complicated, a little harder to see, but here's the idea. So let's look at computing this convolution. So what we're doing in this block, I need 2n data points from x0 to 2n minus 1. Let's call that DFT this. So I'm going to need that DFT, and in this block I will have computed that. And now let's also look here. That needs 2n data points, starting at 2n, going to 4n, right? New data starts at 3n, but the old data is going to start at 2n. That's why we had to jump over that one. Okay, so let's call that x2n to 4n. So notice that the data that goes into this one and the data that goes into this one are contiguous. There's no gaps in between them. And now let's look at this box here. If we follow our little notation, that tells us that it needs data from x0 to 4n minus 1. So let's call that DFT that thing. Now here's the key. Notice that 0 to 2n, 2n to 4n covers that same range. Now I've done a little trick here on the notation. It really just goes up to 2n minus 1, but I just wrote it as 2n. So it looks like there's one point in common, but that's not really true. So keep that in mind. So here's the thing. The prioritization of our algorithm says that before I can start working on that, I should have finished this and I should have finished this as well. Those are my priorities. If I'm not finished with this one, I've got no business working on that one yet. So let's imagine I've finished this, so I have that. I've finished this one, so I have that. And now I'm about to start on this one. So that's assuming I've also already done that one. But remember, those two share the same FFT, so I've already got that one too, right? That was trick number 2. So now I'm ready to start this one, and I've got the 2 DFTs from the 2 subblocks that correspond to the full block of the DFT that I need. So the question then becomes, can I somehow use these 2 to compute that one? And we would have a similar thing between 3 and 5 and so on and so on. So the answer is yes, we can exploit these previously computed half-length DFTs to compute the bigger DFT. And let's see how to do that. So let's just look at it in general for M point. And we want 2 contiguous 2 M over 2 point blocks that make up this M point block. We're going to say we already have those DFTs. So let's take our M point block, say the whole thing is that. That's what we're going to denote it as. That's the DFT we want. But now suppose we take the first half of our signal, I just denote it with a subscript of FH for first half, and the second half of the signal, and imagine taking the DFT, M over 2 point DFT of each of those, and just call those that. Now, these have already been computed because we've already completed the tasks that needed those. So the question is, can I exploit these to enable me to more efficiently get that? That's the question. And so here's part of the answer. For the even points, very easy. You just literally add them together. It's so nice, very efficient. So we can at least get half of the points of this very, very easily. And we have to work harder to get the odd points. So first, we can't do it without doing a DFT, but we can do it using a shorter DFT, as we'll see. We have to form this difference. We have to do this product, and we have to then compute this DFT. So that's what I have down here. You form this difference, you modulate it, right? We're multiplying by a complex exponential. It's a frequency shift or a modulation. And then we compute its DFT. So that looks like there's a little bit more work, and we might think, why do I have to do that? Am I going to end up being ahead? Well, let's take a look. The reason we end up being ahead is that in general, this might not be an advantage, but for us, we can again exploit the fact that these things are real valued. So let's take a look at that. So here's the proof of these above results. There's our full DFT that we want. And now I've just written it out, and I've just renamed the first half and second half. So there's a N over 2 point DFT. There's an N over 2 point DFT, sorta, okay? Because really K is going, or M over 2 point, I should say. But K is really going the whole range, but we've already seen that idea back in the FFT. But let's analyze this and work it a little bit farther. So let's take a look at this thing. Yeah, because technically this second one isn't really a DFT yet. We need to massage it a little bit more. So I've just rewritten that out in terms of explicit exponentials. And now I've just used properties of exponentials to break it down that way. And then I've just used, again, properties of exponentials. The m's cancel. I get the 2's cancel. And so I get a integer multiple of pi there. And then I get this left behind. That's just w sub m to the nk. Okay. So now I can substitute that in. This and this can get pulled out, and it leaves this thing behind inside there. So that's how I get to that form. And we can start to see the thing that I took the difference of. Where does that difference come from? Well, remember that was for the case where we were looking at the even indexes of our DFT result. So that means I'm going to replace K by 2R. So this will be my notation. I'll use a superscript E for that. So this thing indexed over integers is just the thing that I want indexed on the even. I suppose I could have just left that out. I'm not worried about it. But now this K gets replaced by 2R, and I've got a 2 pi there. So 2 pi times an integer is going to just always take me to plus 1. So that thing boils down to plus 1. Oh, I said a difference. It was really the sum of the two. We'll see the difference coming up in just a little bit. And this I've just reworked. That gives me the W form for a true M over 2 point DFT. And so now I can rewrite this way. And so this is the preliminary DFT. This is a preliminary DFT. So I have those. So for the even values that I want, I get it almost for free. Just a bunch of adds, nothing else. Now for the odd points, it's a bit harder. I'm going to skip some details here because I don't want to spend a lot of time on this because we're already over an hour for this note set. But it's pretty clear with a little bit of digging into this that we can use ideas that we've seen before. So now when we plug in 2R plus 1, this thing becomes minus 1. That's where the difference comes from. So we get the sum for the even index points and the difference for the odd index points. So now I have to form this difference, and this thing still boils down. There's a thing that ends up getting pulled out in front there. So we have to form this difference, modulate it. So that's a frequency shift. That's kind of interesting. We need to fill in some holes that we're missing, right? We have the even indexed ones. We need some, and we're kind of shifting things over into that position. So that's kind of how I like to think about this. So we form a difference, modulate it off the grid, and that's what we would get. But we can save further computations because these things are real valued. And again, this is where I'm skipping a few steps, but the idea is that we can compute the odd point DFT for real valued signals with a slight mod to our previous real valued result. So we would form a G from those, just like before, and we could form this full M over 2 point DFT, but we only need the odd points of that. And so with a little bit of extra work that I skipped, we can show that we would compute a M over 4 point DFT and just take the values that are on the odd indices of that. And that's what we would get. And so then we would use this little trick to extract the things that we want. And this again comes from the fact that we're playing some tricks with the odd point. Again, I've skipped over some steps here, but this is if you just follow these rules, it will work. So where does that get us? So here is a figure from Gardner's paper. We've already talked about this being excessive in the number of multiplications that we need to do. We already talked about this being excessive in the latency that it requires. And remember, this is really, out like 100 times that. So it'd be like seconds of latency. What are the other curves that I've now put back on? So when I first showed you this, I removed some of the curves that Gardner had on there. I've now put them all back on. So here is the zero latency optimized zero delay method. This is the method that we just looked at, with all the tricks involved, with the practical decomposition so that we have a uniform demand. So this is the uniform demand approach right here. And you can see that it does grow as the filter size grows, the number of multiplications that we have to do, but it grows pretty slowly, and it should just keep bending over like that. What's the next one below it? Well, that's our impractical minimum cost zero delay method. That's the one where the processor has to sit idle. Well, it's doing the direct for the H0. So it's doing that, and then it has to work like crazy for one sample period and then back to doing nothing, just like you do homework. So we said that wasn't really feasible, even though it does give us a little bit better complexity performance. So what's this other curve here? Well, if we say, you know what, let's do the first block as overlap save as well, rather than direct. Well, we can calculate the amount of latency will be the size of that first block. So if we use n equal to 32, the first block will have filter block will have a size of 64. And if you take 64 and divide it by our sampling rate, we'll get seconds of delay or latency. So that's about 1.5 milliseconds of delay. That's hardly anything to be concerned about. And look, it saves a lot. It's even more efficient than the minimum cost zero delay. And so you can play a game. You could maybe even do a bigger block. If we went to n equal to 64, we'd get double that delay, and we'd probably go even further down. So you can play with that however you want to do a trade-off between computational complexity and the amount of delay that you have. So that's what we accomplished here. A nice algorithm that if we need absolute zero latency, we can get it. If we don't need absolute zero latency, we can give up a little bit of that and reduce the complexity a lot. And that's what Gardner's algorithm does for us. And we covered a lot of ground here. This is the last slide. We're well over an hour into this, but I do just want to go through a summary of the key ideas that led to this. The biggest of them is that not only can we break the signal into blocks, we can break the impulse response into blocks. So once we see that, then each individual IR block can then be used in its own individual overlap save processing. That's the key. Second key idea is that we have to properly choose how we break the impulse response into blocks. And this will give us a nice uniform load performance, not necessarily minimum computation, but we'd rather have the uniform load. Third key idea, if we want absolute zero latency, do the first block using direct form. Fourth key idea, all the other blocks are done using overlap save. Backpedaling just a little bit, if we're willing to give up just a little bit of latency, we can even do this with overlap save. Fifth key idea, we need to have a way to schedule and prioritize all the tasks that we have. And so it will require multi-threaded processing and some complicated programming and all that, but it's what you need to do to make this thing work. And then the sixth key idea is we can be clever and reuse results and figure out how to efficiently compute things for this particular application. So reuse previously computed DFTs whenever we can, fuse two M-point DFTs into one 2M-point DFT. Those are the locations where we would have that. Exploit all sorts of classic tricks for computing DFTs, especially the fact that all of our data is going to be real valued. And that is the end. So hopefully you hung in there. It's a cool algorithm. It's one of those papers that you read and you say, I wish I had figured that out. That would have been a cool day in my career. So that's it for convolution reverb. Next, we will turn our attention to using delay networks for reverb. And that idea goes all the way back to 1962, I think. So that was when it was published, so it was probably being developed end of the 50s, early 60s. So hopefully we will see you there.